Okay. So now we can start with quantum channels. Oh, sorry, with the circuit model of computation. For the circuit model, we're going to need a few. Um, yeah, we'll need to set up the notation a little bit, but besides that, it should be relatively simple. Okay. Okay, so let's start with section 2.4, which is quantum information slash computation. Okay, so um, so we're going to use basically we're going to work with qubits exclusively, right? So qubit is just a two-level system, right? And we're going to use the notation. Okay? The standard basis is 0, 1. Okay, but standard or computational basis, as it's also called, of being 0 and 1. Okay. So we use registers. Okay, so qubits would typically be used denoted with registers X, Y, Z. The notation qubits will be denoted using registers X, Y, Z, etc. Okay, and so for an n qubit register, X, uh, an integer X in 0 to the n minus 1. Okay, so given this n qubit register and some integer X in 0 to 2 to the n minus 1, we use what? We use X belongs to capital X to denote um, the state X1, it's Xn, where each of these denotes the ith bit, where so Xi denotes the ith bit of reiterated in the binary notation. So that's just the notation we use. So here's a quick example. So, so 2 belonging to X means you have, state 1 tensor 1 in the qubits. Okay, good. So this is fine. Now we're going to look at the circuit model. So we're going to define what a quantum circuit is. So definition 63 defines a quantum circuit. Okay. Okay, so we do the following. So let gate set. Okay, so this is supposed to be like nice font. Okay, so let gate set be a set of quantum channels. Okay, and remember, all quantum channels now are assumed to be trace preserving. Okay, and then a quantum circuit relative to this gate set. Let's call it GS. Is an acyclic network of quantum gates and wires where a quantum gate is a channel from GS, okay, and a wire is just representing a qubit, basically. Okay, so each wire represents a qubit. Okay, and what is the gate set that we take? So the gate set that we are taking, so there's nothing particularly special about this gate set. You can take any universal gate set. But the one that we're taking here, and I'll define what I mean by universal in just a moment. But the gate set that we take here is consists of the following, right? So it has. Let me see if there's a better way to represent these. Yeah, so we look at the Toffoli gate. So I'm writing the unitary description of the gates, but you can also write the channels. Okay, so here's what the Toffoli looks like. So you have ABC. So it's a control not. So it adds to the not if both A and B are true. Okay, and you have AB. Does that gate? It has the Hadamard. So it's defined by Toffoli. Hadamard. What is the Hadamard gate? The Hadamard gate, as we all know and love, does what? It sends it to 0 plus minus 1 to the A1 by A2. Okay, so if it's 0, it just makes it plus 1, the plus state, and if it's minus, or if it's 1, it makes it into the minus state. Then there's the phase gate. What is the phase gate? It takes A, apply the phase gate, and it adds a I to the A. Is it either adds I or doesn't add I? Now there are going to be some non-unitary gates. So there's the ancillary gate. Don't necessarily have to do this, but it's just how it's sometimes useful to do this. So here you have the 0. So it basically just produces a qubit initialized to 0. That's the ancillary gate. Or also the auxiliary gate, depending on which term you prefer. And there's the erasure gate that takes rho and traces it out. Yeah, so basically, it's used for partial tracing and so on. Okay. Alrighty. So this is the gate set that we use. Close the bracket. Okay, and what's nice now with this gate set, and actually with many other gate sets, is the following universality. Okay, what's the universality statement here? Okay, so the universality statement is the following. So theorem 64, it's universality. Quantum circuits. As I said, it basically is a consequence of Solovay-Kitaev. And what does it say? It says the following. So let E be any quantum channel. So this is trace prescribing quantum channel from n qubits to n qubits. Then for every uh, every epsilon greater than 0, there is a quantum circuit in that sense, using the gate set that we showed, um, with n qubit inputs and n qubit outputs, such that circuit Q, yeah, such that Q epsilon approximates the channel E. Okay, we haven't formalized what epsilon approximates means. So we'll do it in just a few minutes. But the claim is that for any epsilon that you choose, you can construct a quantum circuit which is epsilon close to the initial quantum channel you were interested in. Okay, and further, for fixed n and m. Oh shoot, I forgot to define the size of the quantum circuit. So size of Q is the number of gates. So maybe I should write this down. So size of Q, I guess is a quantum circuit, is the number of quantum gates in the quantum circuit. Okay, so the size of Q is at most a polynomial log 1 by epsilon. Okay, so even if you want inverse exponential precision, you only need poly many gates. But note that n and m are fixed, because there's no scaling with n and m in the statement. So if you have fixed input sizes, then you can have a number of gates scale polynomially and yet have exponentially precise or exponential precision in how far you're able to approximate uh, the given channel. Okay, so that was the main result that we wanted to mention here. Of course, we are not talking about efficiencies yet. So one can define it. I guess we'll define it when we need it, or I'll maybe add it in the notes that BQP would be, so we'll define. So I'll just write up the story for now. So BQP bounded quantum poly would be, problems that you can solve using quantum circuits of size polynomial in the input size. Okay, so the number of gates are polynomial. So we'll define this a bit later. There's also a nice sense in which you can purify these circuits. So, there are these non-unitary gates, ancillars and erasures. So one can purify these circuits. So for example, yeah, I'll probably leave this to the notes. Okay, so the other thing you can look at, there's like a nice picture that shows that you can purify, quantum circuits so that they're unitary. Quantum circuits so that they're unitary. By introducing ancillars and measurements in the end. Ancillars and postponing all measurements. And you can still implement whatever channel the thing is implementing. Okay.